Hey guys, in this video we are going to discuss Runge-Kutta method, right? So why we are going to discuss this? Because I think you have noticed that. Let me take that note. So in Taylor series method, right? Here this is the Taylor series, the truncated Taylor series, right? So when you find the next iterative using this, right, this, so basically we consider this initial value problem, right? So differential equation and initial value, right? And we consider the part of the Taylor series. This is the infinite series, and we consider part of Taylor series, right? So here if you use Taylor series method to evaluate uh, approximate this function here, right? So for that you have to compute these higher order derivatives, which is very difficult, here. So you want, if you use Taylor series method, right? So one difficulty when you use Taylor series method, you have to compute these higher order terms, higher order derivatives, right? So that is tedious work. So to avoid that, so we use a Runge-Kutta method, right? Okay. So for Runge-Kutta method, if you use Runge-Kutta method, you don't have to compute these higher order terms. Let's see how it does, right? First one, the first order method. So which is same with Euler method. Here this one, this is the Euler's method, right? Here there is no f prime, right? So you have, so this is the recurrence equation. Using this iterative, using this approximation, you find the next iterative, right? So for that, for this first order one, so you just need f evaluated at tk and xk. So right, so the first order Runge-Kutta method is the same with the Euler's method, right? So now let's talk about second order Runge-Kutta method, right? So for second order, so given xk, so suppose this, we know this approximation. Now we find the next iterative, right? Using the previous one. So this is the recurrence equation. So we are using, right? So this is the recurrence equation. This is the second order method, right? The first order method is saved with the Euler's method, right? Right, second order method, and k1 and k2 are defined here, right? K1 is equal to h times f of evaluated at tk and xk. K2 is equal to h times f of these two things, tk plus h and xk plus k. You use this value here, right? So this is the second order method. This is also called Heron's method, right? So the second order method is called Heron's method. Man, it's not that important, right? So this method is of second order. So we are going to prove this method is of order 2, right? So how do you do that? So let's see how we prove this method is second order, right? So in my previous video talked about the local truncation error and global truncation error. So we know the global or total truncation error is one less, so it is sufficient to show that the local truncation error of this method, the local truncation error is of order 3. That means the global truncation or total truncation error is one less. That means order 2, right, is of order 2, right? So for that we want to know, I think we want to know the tail expansion into variables. Let's see how do you expand, how do you use tail expansion for two variables. All right, this is the second degree Taylor polynomial of f for xy coordinate near AB point, right? So f of that point plus the derivative of f with respect to x and the point AB times x minus a, right? So here if you have the derivative of f with respect to x, then this should be x minus a, and the derivative of f with respect to y and evaluated at this point AB times y minus b, and then the second derivative, right? Then we consider the second derivative. So second derivative of f with respect to x evaluated at AB point divided by factorial 2 times x minus a squared, right? And the second derivative of f with respect to x and y evaluated at the point AB times x minus a times y minus b, and this is your final. So this is the second derivative of f with respect to y only evaluated at the point AB divided by factorial 2 times y minus b square plus the big O, so plus the higher order term. This is second order Taylor polynomial of f for two variables, right? Now we use that, right? So this is the Taylor expansion of f at tk comma xk, right? So so the Taylor expansion of f evaluated at this point tk plus h comma xk plus k1 is equal to the point. So because the center is this point, right? tk comma xk, right? This is your first term, and the next term plus, and we have to come and the next term would be the first derivatives. So let's differentiate this with respect to differentiation of f with respect to t. So when you differentiate with respect to t, that means, alright, so this is the derivative of f with respect to t. When you consider that, you have to then this one minus this one minus this is the t component, this is your x component, this one minus t, you have to multiply by that term. That means you have to multiply by h, and the other term plus the first order term with respect to this variable x evaluated at this point, right? And you have to multiply it by this one minus this code, this one here, this one minus this k1, right? So and all the other higher order terms, right? We just consider the first order terms, right? All right. Okay, so here your k1, what is your k1? K1 is your function, the order of k1 is 1, so the order of k1 is 1, h to the power 1, right? So k1 is a function of h, so therefore k1 squared also function of h squared, and this means the order of h squared, right? So yeah, so what is your k2? K2 is h times f of t, yep, yep, f of tk plus h, comma xk plus this one. Subbing that. All right, we found this one, so we have that one. This is the truncated Taylor series. Taylor series truncated one, right? This is the error order of h. So we can h times, we can sub that one, we can sub this one into there. So h times this thing, whole thing, plus the order h squared, right? So we found k1 and k2. K1 is this one, k2 is in terms of f and its derivatives, right? So now we plug those things, those two coefficients into this recursive equation, then we get this one here, right? So here we ignore these parts, right? These things, we don't write tk xk, right? We just write f and h, so and its derivatives, right? So here we have, yep, so xk plus 1 half k1. K1 is h times f, yep, h times f plus yep, this one hf, h squared t first derivative with respect to t, and h squared f first derivative, and plus when you multiply this one with this, get order 3. All right, now you can see that you can rearrange this like this, right? So you can see that, yep, this is the so this is your recursive relation, right? So here this is your exact value at this is the exact value of x at tk plus 1. Now you can write the Taylor expansion. This is the exact value, so this one is also the exact value at tk plus 1. So you can write the Taylor expansion for this, which is x of exact value of x at tk plus and h times the first derivative plus 1 half h squared times the second derivative, right, and higher order terms, right? So you can rewrite this one in terms of so this one is same with f of tk, this should be x of, yep, this should be f of tk comma x of tk, because this is your exact solution, right? And this one also, yep, then the other term, double derivative is this, and plus higher order third order term, right? All higher order terms. and you can rearrange this. You get finally you get this one here, right? And over the three terms, all other order three terms. Okay, so now we compare. This is your exact value, x evaluated at t k plus 1, and this one is your approximation. This is your exact value. Distance between this one exact and the approximated one, you can see that this one coincide. Yeah, so this goes with this one also the same, right? So you can see that the distance between xk, the approximation, and the exact is also the order 3, is of order 3, right? So this is the local truncation. So therefore the total error of this method, Heron's method, is of second order or order 2, right? So because the local error is of order 3, that means the global or total error would be of order 2, one less.